All right, physics reaction number 81. And I just did a search for, I think I may have typed physics lecture notes. I found this, so let's see how it goes.
So last time we were talking about angular momentum, and we're going to continue to talk about angular momentum and how it interacts with torque. So
Cool.
We're going to talk about a very specific phenomenon today. We're going to talk about a phenomenon called gyroscopic precession.
Ooh, excellent.
So first, I want to ask you guys if you've ever been nerd sniped before. I don't know how common of an experience this is, but when I was writing up my notes this morning, or rather fixing my notes this morning, I came upon a really interesting problem in the thing that we're going to talk about today. And then I wasted about an hour and a half trying to solve it. Turns out it's a hard problem. So that's a bummer. But you'll see. You'll see how this gets interesting. It really does, at least from a physics perspective. And this has to do with gyroscopic precession. So I want you guys to think back to like second week of lecture or something like that. When we first started or before we even started talking about circular motion, just an object moving in a circle, we did this thing where we decomposed the acceleration vector that an object has. We decomposed its acceleration vector into an acceleration that's in the direction of motion, i.e. speeding up or slowing down, and an acceleration that's perpendicular to the direction of motion, turning. So we can do the same thing in terms of momentum. So in terms of momentum, we could talk about the change in momentum as either its magnitude or its direction. And remember that the change in momentum, the time rate of change of momentum, is the net force. So in particular, we could write the net force as the change in the magnitude of the momentum times the unit vector in the direction of the momentum plus the magnitude of the momentum times the rate of change of the unit vector of the momentum. This is just the product rule, remember. And so
so this is super, super tough, right? So this idea is actually really, really tough. The idea that the momentum is a magnitude times its direction, and that, oh, well, if that's a product, then we'll just do the product rule to get the derivative. And what happens if you just use x hats, y hats, and z hats, or I hats, j hats, and k hats, they don't have a time derivative, and so you don't actually need to normally bother with that. But if you do, for example, in some polar coordinates or something, spherical coordinates, then suddenly these things do have a time derivative, and that's why the front cover of your E&M book has all of those crazy, ugly expressions for the various derivatives that are involved. So I think this is really interesting. I'm trying to see where he's trying to get to with this. I don't have a problem with this. I'm just not sure. I wouldn't have gotten to gyroscopic precession this way, so I'm super excited to see the connections here.
This is the same thing that we did before. It's just before we had v, we had dv dt. But here the mass isn't changing, so this is just a momentum way of viewing the exact same thing. So this vector here, the time derivative of the unit vector p, indicates that the direction of motion is changing. Whereas dp dt without a unit vector, this characterizes the changing magnitude of the momentum, speeding up, slowing down, that kind of thing.
Cool.
So, and remember that these two vectors were perpendicular to each other.
Just going to pause and talk about the structure of this. So it's using OneNote, which I love, although I got to tell you, I'm not as happy with the updated version of OneNote, and I almost want to just downgrade it to get back to this really cool stuff here. But whatever. But there's a really interesting organizational structure that he's using over here, which is to be not organized. And so he's got this in quick notes. And so it just seems like this is not being saved, and that maybe the video is the currency, right, for this class. And so it seems like maybe he's just treating this as a whiteboard that you write on, you can erase later. Obviously he makes new ones, so these are all there, but they're all called untitled. So I'd be really curious to ask him if how these get used, whether it's worth it to save them. He's clearly writing everything out. Like I was noticing when he wrote this phrase, changing magnitude, I was like, yep, just waiting for him to finish writing the word. And so there's this idea of really starting with a blank page and writing every single thing out versus doing some things ahead of time versus using some old stuff Kind of depends on how much you're hoping your students are taking notes along with you. So some very cool stuff going on.
And we found that by doing some magic algebra. And after, and again, I'm framing this in terms of momentum, but we did this in terms of acceleration. But what we did in order to understand circular motion is we analyzed the perpendicular aspect of the motion, that is p dp dt, dp hat dt. We analyzed what happens when that one's not zero and this one is zero, and that led to circular motion. In particular, we got that this is equal to the mass times the acceleration in the perpendicular direction, which gives us circular motion. The object's speed is never changing, but the direction constantly is. And now that we've actually discussed angular momentum, we can do the exact same thing relating angular momentum to torque.
Oh, okay.
In particular, we can write that the net torque on an object, which is equal to the time derivative of the angular momentum, that's equal to the time derivative of the magnitude of the angular momentum plus the time derivative of the unit vector of the direction of the angular momentum.
Very cool.
And so in particular, if L, the magnitude, is held constant,
so, sorry, this word held, if L is held constant, normally I think that phrase came about when we were literally holding the height of something or holding it back from being moved horizontally. I actually don't think that's the right verb for angular momentum. I think that it's the universe that shows us ways to keep the angular momentum, the magnitude of angular momentum constant. I'm trying to think of if held is the verb that makes sense there. I mean, I totally get why he says it. That's the verb we use all the time. But it's hard to say, hey, here's something, hold it at a constant magnitude of angular momentum, versus here's something, hold its x value to be constant, just hold on to it, or its y value, right? But I guess I never thought about that before. It just sort of jumped out at me when he said it and then he wrote it. So I'd love to hear your thoughts about that.
But the direction is changing. The direction meaning the unit vector. We might similarly expect some sort of circular motion, just a different kind.
Okay.
Just in the exact same way that we found circular motion in the regular momentum and force case.
Wow, okay.
So in this scenario, we
cool.
have that the net torque is equal to L times dl hat dt. And that's because the magnitude isn't changing, so dl dt is 0.
Yeah.
So the question is how do we build a system? How do we build a system like this? Like what would be a good example? So to build a system that, and the reason why we want to do that, by the way, is because we want to investigate what happens when you have the same sort of phenomenon occurring for rotational motion.
And I was just noticing this vent in the ceiling, and how whenever I see vents in the ceiling, I think about living in the South. Because often in Minnesota here, we don't, I mean, I'm sure they exist, especially for air conditioning, but because heat rises, almost all of our vents are down at the bottom, because heat is you absolutely must have in Minnesota, whereas air conditioning is a nice thing. And if it's all centralized and you're going to just put a vent in one place, you tend to want to put it down below. So I'm going to make a guess that he lives in the South based on that tiny little clue. Sorry. Hey, that's thermodynamics. It has to do with physics.
To build such a system, we need, or rather, we notice that dl hat dt as a vector is perpendicular to the momentum vector. So we need a system.
Let me pause for a second. Does dl hat dt have to be perpendicular to L hat? Well, it's a unit vector, so it can't grow. So any change has to be perpendicular. Yep, that's cool.
Where the torque, because the torque is proportional to dl hat dt, where the torque is perpendicular to the angular momentum. And that would be like saying, in the case of regular circular motion, like an object, like a rock tied to a string going around in a circle, the force, which is the tension force on the rock, which is pulling it towards the center, is perpendicular to the momentum vector, which is going along the circle, right? Those two are perpendicular. We need the same thing here. We need that the torque is perpendicular to the angular momentum.
Cool.
So we can just try to come up with an example. There's a standard one that we're going to go over, and it involves...
So the other way, I think, to drive that home is if the torque is perpendicular to the angular momentum, its magnitude is not going to change. It's like the backwards way of saying what he's saying. But I'm really liking this analogy. So I see where he's getting to, right? Because precession is thing going around in a circle, but it's a weird thing going around in a circle, right? It's the thing that's already spinning in the first place. And then its axis of spin moves around in a circle. And so it is sort of one step removed from typical circular motion. And so he's doing this wonderful analogy to build up to it. Man, this is super cool.
Involves a gyroscope. So there's actually a neat video, but I'm gonna put off watching it. Actually, no. Let's try this. I'm just gonna try to skip along to the. I don't want to give away the explanation, but. I think it's here. I'm gonna share a new screen. It's Veritasium, excellent YouTube guy. Hopefully you guys can hear this.
Point there. So if I let go, well, it does exactly.
Sorry,
So in the show that I do at elementary schools, I bring up a third grader, and I have them sit underneath this. So let me just, well, can I go back? Yeah, I have them sit like right down here. And I say, hey, would it be okay if I let go of this? And they're like, what are you kidding? And then I have them move, and I drop it just like what Veritasium did, what Derek did here. And sure enough, it gets smacked, And so then I go through all of this notion about exactly, what we're going to learn about here. And I spin it around and I have it do it again. Sometimes that student's a little scared, but, of course, it just precesses around. It's so cool. And what we did when we built ours, we knew that the higher the moment of inertia, the cooler this was going to be. So we took the inner tube of the tire and we cut it open. We filled it full of shotgun pellets. They actually might be lead for all I know. And so our tire is so heavy. I mean, it's a beast. And then we have these nice little handles on there. And I tied a rope on the end of it. And oh my gosh, you get that thing going. You could leave it going all day long because it had such a high moment of inertia. All right, let's get back to it here.
So if I let go, well, it does exactly.
Sorry, I'm still skipping around. Oh boy, my tablet can't handle it. Yeah, no, we are very much dropping FPS. I just want to show you an example of it happening. I would normally do this in lecture, but I can't. Okay, here we go. He's doing it. Okay. This is the kind of thing that we expect to happen.
It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque.
So this is the kind of thing that we're going to try to understand. That it's a standard physics demo, and I would suggest that you watch the whole thing. It's a great explanation. But for now, and it's linked in the lecture. It's linked in the lecture notes. But for now, that we're going to do our own analysis of that. Hopefully the frames aren't dropping now. Yeah, sorry. It is really cool though, and I would have loved to have done this in person. We will talk about biking as well. Right. So the picture here is.
So this seems to be live-ish, because he seems to be responding to something off screen. I wonder if it's like chat from his students. Oh, that's really cool. I didn't realize that. So cool. Yeah, that Veritasium stuff is great. I remember when Veritasium has this video about this gigantic like cement sphere that floats on water. And so he and I went back and forth about that. And then later when I interviewed him, it was just so fun to talk to him about his his thesis work, which you should check out. Super, super cool, because honestly, it has everything to do with how students learn from video. So check it out for sure.
So we have so the example really is gyroscopic precession. That's really what we're talking about. So the picture here is you have some pivot maybe. You have a rod or an axle attached to a wheel. Coming out, say, the other side, just like a bike wheel or whatever. The wheel is spinning maybe this way with some angular speed at omega.
Cool.
And there's a few forces at play. So first of all, there's going to be a force on the center of mass of the wheel due to gravity. It's a force straight down. By the way, I'm going to extend this out just so then it's a little bit easier to see. And I'll draw this so that's more obvious. So imagine that this is just like resting on the ground or something, right? The wheel's not touching the ground, the thing it's resting on is. There's a normal force pushing up the pivot, say here. But in principle, like assuming that the wheel is, attached to the pivot point, that's really all the forces that are present. And you might intuitively think, well, okay, the wheel's just going to spin and it's just going to fall down, right? But that's not what happens, as we just saw. It's actually kind of amazing what happens. So let's start analyzing this from a rotational perspective. So from the right-hand rule, and by the way, this is supposed to be like rotating, like this side is supposed to be further outside or like closer to you, and this side's supposed to be further from you, just so then we can get the perspective right. So from the right-hand rule, we can automatically...
Sorry, I was just muttering under my breath right there. I remembered something that it was almost like a traumatic memory when I was doing this show once with some students, and I would hold the wheel and I would spin, and I would just hold it and show the students how hard it is to sort of turn it. And I always wanted them to see that if they tried to move it, I can't remember, to the left, that it would kind of dip down, right? And so I spun it, and I handed it to the student, but I didn't hand it to them this way. I just gave them the other handle, and I told them to turn, must have turned left or whatever, and it spun up. And the wheel came up and hit their chin, and I had to grab it, and oh my gosh, I needed a Band-Aid. It was so embarrassing, and everyone was pretty upset. And so we had to sort of stop the show and help the student, and I really felt bad. And of course, my only mistake was a twist around, right? That I added an extra negative sign in the analysis, and instead of it going down, where every time I'd done it before, students just kind of goes down, and they just sort of say, whoa, that's weird. But if it goes up, it came up and hit her face. So I was just realizing I was muttering. I was like literally reliving that experience. I'm like, oh my God. So sorry about that. But it's so interesting to think about how many sign mistakes you can make in problems like these. And so, just looking at this here, honestly, I'd have to do a tiny little bit more sort of right-hand rule stuff to figure out which way this precesses. I don't think there's a natural way that I have found to remember which way it's going to go. So I'm trying to think. Obviously, there's my memory of how I do this. I think we're going to have to follow along this right-hand rule stuff he's doing.
They figure out what the direction of the angular momentum is about the central axis here of the wheel, right? It should be pointing to the right. So hands rotating in the direction of the wheel, thumb points in the direction of the angular momentum. So we have that
it's gonna go,
the angular momentum points up to the right.
It's going to go, this will go into the page.
Now, we don't necessarily want to find the torque about the center of mass because that would be confusing, just because there's a normal force over here. It turns out that the normal force is going to be the exact, or the torque would be the exact same anyway. But let's imagine the torque from this pivot point over on the left here. We're going to try to find the torque there. Well, so we have to use the right-hand rule. We do R. So the normal force doesn't contribute to the torque because it's located at the place where the pivot point is.
Gravity's going to be into the page.
So the net torque is going to be R.
Which
the
is going to
vector R
knock
points from the pivot
going
to
to try to
the
get
force
the
supply.
angular momentum to go into the page, which means it's
R
the
cross
tip of it's
F,
going to go
which is
into the
down.
page.
So in this case, the torque, I'm just moving my thumb so you can see it, the torque points into the screen, notated this way. I think I've used this notation before. This is...
Whoa, I wasn't watching him. This is actually really hard when you're on video. Let's go back and watch him now. Because I was saying into the page. Did he also say into the page? So first of all, we don't think he's flipped because most people are right-handed. He's writing with his right hand. So
is going to be R. The vector R points from the pivot to where the force is applied.
what?
R.
Okay, think about what he's doing right there. If that's how he sees it, that's not how it's drawn. Ugh. Is he mentally doing the right conversions for his students?
Cross F, which is down. So in this case, the torque, I'm just moving my thumb so you can see it, the torque points into the screen.
Hang on, let me watch myself do this. I would have done, so this is my right hand. I would have done that way, which looks to be the wrong way on the screen. Then I would have gone down, and I would have gone into the page, which is into the camera. What if I'd done it with my left hand accidentally? I would have made my hand go like that, would have gone down, and oh my gosh, how did he do that? That was cool.
Notated this way. I think I've used this notation before. This is like the backside of an arrow with.
I'm actually going to stop. Just notice the time. I don't like these things to get too long. Super awesome stuff. I really, really love this analogy he was doing. And now that at first I was like, what is he doing? But it totally makes sense because circular motion by itself is hard. And to explain this like extra other circular motion, this precession stuff, this analogy I thought was really, really cool. And then the work he's doing here in the video that he showed, I thought was great too. Awesome. Awesome. All right. Well, you guys, I hope you have a great day. And remember, physics teachers are awesome.